Today we're looking at a couple of different things. One of those things that we are looking at is the concept of shielding and exposure. So we talked a whole lot about radioactivity in our last class and the different types of radioactive materials, the different ways of radioactivity overall. And now we're going to talk about a little bit more about protection. So one of the ways that we can protect ourselves from radiation and from radioactive particles is something called shielding. Shielding is just literally putting a barrier between ourselves and the radioactive materials. And the result of that shielding is that the substances that are radioactive, because they cannot penetrate those shields, will more or less just stay on the surface of those objects. Now, when it comes to the modes of exposure, there are two primary ways that we can be exposed to radiation. First, we can ingest the radioactive material. That is the primary hazard. That is the most dangerous way that we can go and work. Obvious issue with that is once it's inside our body systems, there's considerably less protection available. And so the damages tend to be much more significant. One way to prevent this is the use of self-contained breathing apparatuses. So if you are wearing a scuba mask or some kind of personalized breathing machine that provides full coverage around your face and nose, that would protect from ingestion or inhalation of radioactive particles. The second type is something that is much more common, skin absorption. So for skin absorption, we are looking at those different modes of transmission. Alpha particles are blocked by your skin. So your skin is adequate protection against alpha radiation, unless you have large open sores on your skin. Obviously, those are not as protective and can make your way in through those. Beta particles are capable of penetrating the skin. Full turnouts for people like emergency responders are not sufficient generally for beta particles. Usually we need, again, some form of aluminum or some kind of denser material than fabric to fully provide protection for those beta particles. For gamma rays and X-rays, we've talked about this before, lead and concrete. And generally speaking, lead is denser. And so since it is denser, it requires less. So several inches, at least 3 inches of lead are generally recommended for blocking gamma rays. For concrete, it's usually on the order of feet. So shielding is one way that we can protect ourselves and have other people be protected from radioactive materials. And here's kind of an illustration of each of those. So again, alpha particles are relatively easily blocked. They can be blocked by your skin. They can be blocked by your clothes. They can be blocked by paper. Beta particles will penetrate those things. But if we get a significantly thick piece of aluminum, and significantly thick can be just like heavy duty aluminum foil, thin sheets of aluminum like sheet metal, that's usually enough to block or at least slow down significantly the beta particles. For X-rays and gamma, they'll easily penetrate any of those objects. Only way we can really stop them is with lead. And usually we need a couple of inches of lead to do it. So one of the things that you will be doing in lab on Friday is you'll be looking at alpha and beta and gamma decay. We have these little discs that have small amounts of those radioactive particles in them. And they really don't pose any danger to you specifically. The quantity is so low that the radioactive dose is insignificant. However, with a Geiger counter, we can detect how many particles are being presented. And we have a number of different kinds of shields that you can put between that radioactive sample and the Geiger counter to see how effective that shield is. So we've got things like, plastics and wood and aluminum and lead, and we've got them in various thicknesses as well. And what you'll see is that the gamma radiation is really hard to block, even with some of the thicknesses of lead. A piece of lead that is, only, quarter-inch thick is definitely going to slow down gamma, but it's certainly not going to block all of it. And you'll see that in the Geiger counter. So shielding is one way we can protect ourselves. Another way is something called the inverse square law. The inverse square law refers to distance. And what it says is that radiation is not a single beam of product, but rather it starts to funnel out in all directions. And so as it goes from the source outward, the number of radioactive particles that you encounter is going to change based upon how far away you are. Closer you are to the source, the more you are toward the neck of that funnel, the more radiation you're going to see. The further away you are, the more you are toward the top of the funnel, the less radiation you're going to see. And we can actually quantify that radiation in terms of its intensity based upon what is called the inverse square law. What the inverse square law says is that the intensity that we see is related to 1 over the distance from the source squared. So the easiest way to think about it is, let's say that, just for the sake of argument here, our distance from the radioactive source is 5 feet. So 5 feet away from the source, I'm going to see some amount of radiation. If I turn that 5 feet into 10 feet, I'm going to see less radiation. I've doubled the distance away, but I haven't doubled the intensity or cut it down by half. I've actually cut it down by a quarter. So when I double the distance away, the intensity goes down by a factor of 4. If I would go back another 5 feet, I've tripled the distance, and the intensity goes down by a factor of 9, 3 squared. So the further away I get from the source, the less damaging it is, because the less radioactivity I ultimately encounter. So shielding and distance play a significant role in terms of how much radiation we actually absorb. Now, in terms of what happens to us when we absorb that radiation, well, there are a number of factors that go into that as well. So, what type of radiation are we talking about? Are we talking about alpha radiation? Are we talking about beta radiation? Are we talking about gamma radiation? How energetic is it? Those kinds of things are going to impact what we ultimately see. What about specific radioisotopes? So some isotopes tend to congregate in different parts of your body. Iodine-based isotopes tend to find their way around your thyroid gland. Reason why? Iodine is one of the things that helps your thyroid gland go. So radioactive isotopes of iodine also tend to end up in your thyroid as well. The difference there is that, well, the normal iodine that you get from iodized salt helps your thyroid gland to function properly. The radioactive stuff will actually start to harm your thyroid gland and could lead to things like thyroid cancer. A person's age has a significant impact. In particular, we see the very young affected more by radiation than older men and women. And the main reason why, young people are growing. And so as they're growing, if they get exposed to a radioactive source that mutates their DNA, that mutation is going to be much more significant because their body's cells are dividing more rapidly and changing more rapidly and growing. And so we see larger impacts faster in children than we do in adults whose metabolic cycles and overall cell growth and decay and interchange are significantly low. So with regard to the specific radioisotopes, I already mentioned iodine because of the thyroid particular issue. Isotopes of strontium and radium have been very strongly linked to leukemia in many patients. So those kinds of situations, those kinds of isotopes do have that particular effect. I'm going to go out on a limb here. I do not know this for certain. You can fact check me if you want. I know that Marie Curie, Madame Curie, one of the foremost leaders in radioisotope research in the early 1900s. Most of her work was done with radium, radioactive material that's found in certain kinds of rocks. Her passing was largely due to her radiation exposure. And so, again, I don't know this for certain. I could be correct, I could be incorrect. But given the radium and how quickly she deteriorated, it could have been a leukemia-like cancer that ultimately caused her to die. Not much was known about radioactivity in her day. She and some of her colleagues were among those who largely discovered radiation and were doing a whole bunch of research without proper protection because they didn't know they needed it yet, to determine what this stuff was and what its potential was. As I mentioned before, the age of individuals does make a difference. Radiation exposure does tend to impact young people more than old people because their cells are dividing much more frequently because they are growing, because they're developing into older children and eventually adults. Once we hit adulthood, once we go past puberty, our cell functions do slow down significantly, which means less cell division and less chances for mutations to really propagate themselves significantly. All right, let's talk about work. As with so many other things, OSHA is required, or excuse me, OSHA requires that any workplace that deals in radiation of any kind must properly and conspicuously post signs showing that there is radiation in this particular area. Now, OSHA has designed the signs, and I'll show them to you in a minute, that it's pretty hard for them not to be conspicuous. Conspicuous just means that they stand out. Only thing your employer has to do is make sure that it's put in an area where you can actually see it. But there are three different types of signs. There is the radiation area, which indicates that there are radioactive particles in this area and proper protective equipment is necessary to enter the area. There is high radiation area, where we have radiation in much higher quantities, higher doses, and therefore that might require different kinds of turnouts or different kinds of equipment. And then there are airborne radioactivity areas where, in addition to maybe a lead vest or a certain type of turnout, you probably are also going to want some kind of self-contained breathing apparatus, or at very minimum, some kind of barrier that covers your face as well. Now, like I said, these signs are conspicuous. They stand out very, very, very easily. They are bright yellow with bright pink letters and pictograms. If this sign is put anywhere in your vision, you will see it. And that's the point. Like I said, it's up to your employer to actually post it in an area where you can see it. And usually these are on like the doors and the windows of the place. Usually in multiple places, honestly. So this is the radioactive material sign. This is the radiation area sign again. So this would be put on the material itself. So if you have a radioactive medicinal or some other kind of material that is radioactive, you would put this on the secondary label. This is for a radiation area. For a high radiation area, notice that the two signs are not all that different. We have kind of bolded the caution there to indicate additional danger. And you'll notice that we changed the signal word for the airborne radiation. Remember, the difference between caution or warning and danger is an increased level of awareness. It is more dangerous in the airborne radioactivity area than it is in the high radiation area. This one was not on the list, but it is a possibility. And you see we've added a couple of extra words to indicate the elevated level of risk. So if and when you are exposed to radiation, what happens? Well, the first thing that happens, our primary action, is that as the substance passes through you, it is going to ionize the matter that it encounters. Again, what we talk about with ionization Again, it is electrons being ripped from the matter. So as the ionizing radiation goes through whatever it encounters, it's picking off little electrons as it goes. As we know from chapters 4 and 5, electrons are what drive bonding. And so if we take electrons away from a substance, it is going to be much more likely to want to replace those electrons through chemical bonding. And so as a result, your body starts to seek out other means of acquiring those electrons. And so the processes that end up ensuing will disrupt your metabolism, will disrupt your other biochemistry processes. And as a result of these, we can see damage to genetic material. So it can impact your DNA. It can potentially mutate your DNA, turn it into something that was not intended. And depending upon those mutations, we can see things like rapid growth, cancer, or just necrosis. The cells die. And then your body has to deal with the dead cells. So that's the primary action of the radiation. That's what happens first. In a secondary manner, we can also see radiation being used for commonly good purposes. Things like medical imaging, where we use those radioactive isotopes to track certain materials as they go through your body and check for problems. So, for example, gadolinium-153 is a very common radioactive nuclide, and it is used in a type of imaging called SPECT. Small radioactive atoms like carbon-11, nitrogen-13, or oxygen-15 are used in PET imaging. PET imaging is positron emission tomography. So these particular substances all emit positrons. So they undergo beta decay, and the tomography can analyze and check and see where those positron emissions are coming from, and pinpoint things like tumors or other kinds of abnormalities in a person. Now, why do we use these particular isotopes? It's relatively simple. We can get good images using these isotopes, using small amounts of these isotopes that yield small amounts of radiation and have small half-lives. Now, why are those three things important? Well, if we get good imaging without having to use a whole lot of radioactivity, that's obviously a positive. The low-level amounts of radiation mean that it's going to be relatively limited in terms of being a harmful substance to your body. And by having a short half-life, we know that it'll be out of your body in a relatively short span. These particular isotopes have half-lives on the order of hours or minutes. So within a day or so, the radioactive material is out of your body completely. Since it doesn't give up a whole lot of radiation in general, it's generally a decent kind of trade-off. We get the imaging without harming the patient significantly. Here are some examples of the types of images that we can get from those. So SPECT imaging in this case is being used in examining a person's brain. PET imaging here was being used and actually pinpointed a growth of cells where there shouldn't have been a growth of cells. So that circled spot on the image is actually a tumor that was identified using PET imaging. All right, so we will stop here for today. Friday, we will talk about nuclear power plants, how nuclear power and nuclear weapons are developed in terms of what kinds of processes they undergo,